Hi, SUPA people. Today we're going to work on a little bit of stuff on solutions. Shouldn't be too bad today. Most of this should be review for you. Right, so let's go ahead and start with solutions. And a solution is a mixture of substances that has a uniform composition. So our solutions are homogeneous mixtures. Okay, remember homo means same. Okay, so these are mixtures where it looks same throughout the whole thing. All right, now solutions, generally when we talk about solutions, we generally think of liquids, but solutions come in all phases. All right, so these come in all phases. So we have solid solutions, and I think we've talked about these. Okay, so solid solutions are generally our metal alloys. So stuff like brass, which is a homogeneous mixture of copper and zinc. I don't know, rose gold. Okay, so there are different colors of gold now that we can get in our jewelry. So this rose gold is really just a solution of gold, copper, and silver. Right, and depending on what color you want, we can change the different composition of these elements to change this different color. So if we want more of a white gold, right, we'd have more silver than copper. But if you want that red gold, you'd have more copper mixed in with the gold. Right. Another example might be steel. Okay, so that's a homogeneous mixture of iron and copper. No, not copper, carbon, excuse me. And steel has some other things in it. It's got some manganese and things, but generally it's mostly iron and carbon. So these are all homogeneous mixtures that are solids. Of course, we have liquids, okay, that are solutions. And these are the ones that we're most familiar with. They're the easiest to work with. All right, remember, if it's a homogeneous liquid, we're really talking about aqueous solutions. Okay, so like our salt water, okay, which would be NaCl aqueous. I don't know, we could talk about copper sulfate aqueous. Okay, so we've talked about these solutions before. And then finally we have gas solutions. And if you have a mixture of gases, you're going to have a solutions, because those gases are all going to expand to fill their container, and they're going to homogeneously mix. So if you have a sample of oxygen and a sample of nitrogen in the same container, all right, those two elements are going to homogeneously mix, and those gases will be a homogeneous mixture. And I guess the most famous gas solution is really just air. Okay, this is just a homogeneous mixture of mostly nitrogen and oxygen. Right? Little CO2, little H2O, a little bit of argon. Right? So our atmosphere, or air, is just an example of a gas solution, right, with all these different elements, and they're homogeneously mixed. So just don't get caught in the idea that solutions are just liquids, because they do come in all three phases. Now, I'm going to perpetrate this problem because we're going to talk mostly about liquid solutions because it's really hard to work with metal alloys. Right? You know, there's not much I can do with a piece of brass, okay? And there's not much we can do with gas solutions. It's a lot easier to work with liquids, so we're gonna talk a lot about liquid solutions. So when we're talking about liquid solutions, we'll talk a little bit about the different type of liquid solutions we can have. So, and the first one we're going to talk about is a saturated solution. And this is a solution in which undissolved solute and dissolved solute are in equilibrium. And we'll talk more about that in a second. In other words, if we have a saturated solution, the solute cannot hold any more salt. The solvent, my gosh, cannot hold any more solute. So the solvent's the thing that does the dissolving, or solute's what we're dissolving. So let me give you an example. All right, so if we take, let's say that I take a beaker, right, and I put some water in it. Right, and I take some sodium chloride and I throw it in. All right, we throw the sodium chloride in, it dissolves, and we get Na pluses and Cl minuses, right, by molecule ion attraction, or that. So we get this dissolving, and then we throw some more salt in and it dissolves, and then we throw some more NaCl in and it dissolves, and we throw some more in and it dissolves, and we throw more in and it dissolves, and we keep throwing the NaCl in and we keep throwing it in, it keeps dissolving. Eventually this gets to a point where it doesn't dissolve anymore, and we start to get this layer of salt on the bottom. Okay, so this is NaCl solid. Okay, so we have NaCl solid dissolving, and we get Na plus aqueuses in here and Cl minus aqueuses. Right? And this dissolves, and we get Na plus aqueuses and Cl minus aqueuses. Now, eventually it won't dissolve anymore, but this comes to what's called an equilibrium. Right? It doesn't stop. It's a dynamic equilibrium. Now, we can't see this happening, right? But it is. So eventually what starts to happen is we have NaCl dissolving into Na plus and Cl minus, but at that same time, an Na plus and a Cl minus will come back together and form NaCl solid. Okay, and a Cl minus and an Na plus will come together, okay, and we get this dynamic equilibrium. So at dynamic equilibrium, the rate of dissolving is equal to the rate of crystallization. And this is how we define a saturated solution. So it can't hold, this liquid can't hold anymore, all right, but it's in an equilibrium with the solid and the liquid, or the solid and the dissolved ions. So this is what's a saturated solution. All right, well, our second type of solution is an unsaturated solution. And this is a solution containing less solute than a solvent can normally dissolve. So if we go back to our example up here, when I first had this beaker of water, when I first threw the NaCl in, it all dissolved. That would be considered an unsaturated solution, because when I threw more NaCl in, it dissolved. And when I threw more NaCl in, it dissolved even again. All right, so if the solution can hold more solute, okay, that's called an unsaturated solution. It is not at equilibrium. And then finally, our last type that we need to talk about are supersaturated solutions. And this is a solution that contains more solute than the solvent can normally hold. So now we have extra solvent in there, or extra solute in the solvent, excuse me. Now, these supersaturated solutions are really hard to make. Right? They're very unstable. Okay, they're very unstable. Okay, generally, what's going to happen is they're going to precipitate and go back to saturation. All right, they don't want that extra stuff dissolved in the solution. Now, how do we make a supersaturated solution? Well, we'll talk about that in a few minutes because it's got to do with temperature. Right now, I'm going to post a video on this. Usually I do this demo. Right, so usually I do this demo, but make sure you watch the sodium acetate demo. Okay, and it shows you a supersaturated solution going and what happens when it goes back to saturation. So make sure you watch this. Right? Okay. So let's take a quick look at this. And this is from the Regents reference tables, and this is some solubility curves. Right? And what I want to do is I want to focus on this line right here. And this is actually the solubility of KNO3, potassium nitrate, in water. All right. And we have a graph of temperature and solubility. Right? And we're going to talk a little bit about that in a few minutes. But what I want to talk about is how much does dissolve. Now, if we're on this line, okay, if we're somewhere exactly on the line, okay, that's how much solute can be dissolved in 100 grams of water at a very specific temperature. All right, so if you're on the line, okay, it's going to be a saturated solution and will be at equilibrium. All right, now, if we're looking at the line and we figure out that we're above the line, so let's say, right, here's my line, and let's say we have this much dissolved, which means we're above this line. That would be a supersaturated solution. We got extra stuff in there. Right? Now, if we're below the line, so let's say that we're down here, below this line, okay, that means we can dissolve more at that temperature, which means this would be an unsaturated solution. Right? So this is just an example of solubility curves, and we'll come back to this in just a few minutes. So let's talk a little bit about solubility and temperature. the solubility of solids in liquids usually increases with temperature. In other words, as temperature increases, as the liquid increases, it will dissolve more and more and more and more and more. Right? And that's actually shown in these solubility curves for the most part. So if we look at most of these, most of them are going up. Okay. So as temperature increases, it will dissolve more and more and more solute. Now there are some exceptions. Okay, ammonia is one of them. HCl is another one. Right. SO2 is another one, but most in general, as we increase temperature, the solubility of solids and liquids will increase. Now, it's different for the solubility of gases. What we got under here? The solubility of gases and liquids decreases as temperature increases. Okay. As the temperature increases, it holds less and less and less and less gas. Right? So the solubility decreases. Now, so I don't know if you've ever done this. So have you ever actually, I don't know, had a soda, right? Gone to the fridge and gotten a soda. You take it out of the fridge and you open the top and you let it, you put it down and you go and you do something for a little bit. Right? And you come back and the soda's warm and you take a quick swig of it and it's gotten flat. Well, one of the reasons it's gotten flat is that as the temperature goes up, the solubility of the carbon dioxide in that soda goes down, so it comes out of the soda. So as your temperature of that soda increases, the carbon dioxide comes out and it becomes flat. Right? So that's just what happens with gases. Right? So temperature is one issue with solubility, and the other one is pressure. Well, first of all, changes in pressure really don't do anything with solids and liquids. Right, so changes in pressure really don't affect how much solid or liquids will dissolve into each other. Right? But they do. Pressure changes do have a major effect on gases. Right? As pressure increases, the solubility of gases in liquids also increases. Okay, so if we increase pressure, more gas will dissolve into the liquid. If we decrease pressure, okay, the solubility of the gas will be less and gas will come out. Now, again, you can actually see this in your soda. All right, so have you ever taken, all right, let's go back to our soda can. You take your soda can, all right, and the first thing we do is we go, psh, and we pop the top. And as soon as we've popped that top, what have we done? Well, what we've done is we've actually decreased the pressure in that can. Okay, so if we go, psh, and then we quickly pour that soda into a glass, what do you see? Well, you see it fizzing away. Okay. That fizz is the carbon dioxide that's coming out of the soda. Right? And the reason it's coming out is we've decreased that pressure quite a bit. And once we decrease that pressure, the solubility of the carbon dioxide goes down, right? And it comes out of the soda. All right, just some examples. All right, so the next thing I kind of want to talk about with liquid solutions is I want to just kind of run through concentrations. Right? And we've done most of this. Actually, I think we've done almost all of it. Right? So most of this should be review, but make sure that you can handle these. And I've given you some questions in the textbook to work with these. All right, so let's say this is expressing solution concentration. Okay, expressing solution concentration. There's actually lots of ways that we can do this. All right, so when we're talking about concentration, we could talk about percent mass, okay, which remember is the mass of the part over the mass of the solution. Times 100. Okay, so we could talk about percent mass. We could talk about parts per million. Okay, ppm, parts per million. Right? This is really the same thing as percent mass, except we're talking about dilute solutions. So this is mass of the, okay, this is still mass of part of solution over the total mass of the solution, except this is times 1,000,000, okay, which is 10 to the 6th. Okay. So we use parts per million when we're talking about dilute solutions. You can actually get into parts per billion, ppb. And it's the same exact as these, except instead of multiplying by 1,000,000, we're going to multiply by 1,000,000,000. And these are for very, 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 very dilute solutions. Right, and we'd multiply by 10 to the 9th. Okay. So these are 3 ways that we can express concentration. Another way we can express concentration is mole fraction, or chi. And remember, our mole fraction is just the moles of the part over total moles. Okay, so we can express concentration using mole fraction. Probably the biggest one that we use is molarity, and we've used this already. And remember, molarity is capital M, and molarity is moles of solute over liters of solution. Remember, a lot of the times you might have to use the density formula. Density equals mass over volume to get some volumes and things. So, right, so this is often related with molarity. Probably this is the most common one to use for concentration. There's one more that we have to deal with, and that's because of colligative properties that we're going to talk about next time, and that's called molality. And it's little m, molality. And molality is moles of solute divided by kilograms of solvent. Okay, kilograms. This is one we have to be in kilograms for. All right, so this is important when we're dealing with colligative properties of solutions, and we're going to be using this one later on. All right, so these are all pretty easy, and we've used most of these. I don't know that we've done a molality. Well, I think we did. Okay, I think we've actually talked about molality. All right, but I just want to run through these because these are different ways of expressing solution concentrations, okay, that we're going to need. I thought I'd do a quick problem with you on this, all right, because you could see something like this. Let's try a problem. We'll do this problem, I think, and I think then we'll call it a day. All right, so an aqueous solution of HCl contains 36% HCl by mass. A, calculate mole fraction of HCl in solution. And B, let's calculate the molality of the solution. All right. Well, it doesn't give us much to go by. So we know that we have an aqueous solution of HCl, which means we have HCl and we have water. All right, so that's our mixture. We know that 36% is HCl, all right, and the rest is water. So we can actually make some assumptions of our solution. So this is going to look familiar, hopefully. I mean, I haven't done this in a while, but all right. So let's just assume that we have 100 grams of the solution. Well, if that's the case, that means we have 36 grams of HCl and we have 64 grams of H2O. All right, well, now that we have that, okay, we're trying to get to mole fraction. And remember, our mole fraction is just the part of moles over the total moles. So what do we have to do with this? Well, we're going to convert these to moles. So number of moles equals our given mass over our gram formula mass. And let's do HCl first. All right. So the number of moles is equal to 36 grams over 36 grams per mole. All right, so it turns out that we have 1.0 moles of HCl. Okay, and then we'll do our water. So now we know how many moles of each one we have. So now our mole fraction, or chi, is equal to the moles of HCl over our total moles. So we go 1.0 moles over 4.6 moles. And we get a chi, or a mole fraction, of 0.22. Okay, so that would be our mole fraction right there. Pretty easy. All right, and then the last thing is to calculate our molality. Well, our molality, or little m, was equal to moles over kilograms of solution. Well, we know how many moles of HCl we have now, so we have 1.0 moles. Okay, our solution, or solvent, not our solution, our solvent. We had 64 grams of solvent. I'm going to convert that to kilograms. So we have 0.064 kilograms of H2O. And our molality would be 15 small m. So this would be called 15 molal solution. A 15 molal solution. All right, so I think that's where we're going to stop for today. Okay, I got some work for you, and we will pick up with this next class.